So we'll get started in maybe a couple of minutes or so. All right, let's get started. So, welcome everyone to day 2 of Blockchains plus TEs. So this is our first workshop in the series of Blockchains plus X, and we are focusing on research and practice at the intersection of trusted execution environments and blockchains. So as we all know, trusted execution environments provides us with a source of trust within hardware, and in the context of blockchains, they find several applications in the design of consensus protocols, mitigating MEV, and perhaps even improving cryptography protocols. And we had an excellent day yesterday where we had 5 different talks and a panel where we discussed the intersection of blockchains and TEs in the context of consensus protocols. We saw how to use trusted hardware by a talk from Mick, how it is used in cryptography as well as relationships to MEV. So today again we have an excellent series of talks. The session today is split into two. The day today is split into 2 sessions, and the first session will consist of 2 talks and a panel, and the next session will consist of 2 more talks. So with that, let's get started with our first talk. Our first speaker is Nick Hines from Oasis Labs, and he's going to talk about a privacy layer for Web3, discovering how to unlock the potential of Web3 with Oasis privacy layer. Nick, do you want to share your screen?
Cool, thank you, Carter.
Get started.
Cool, share my screen now. So in a bit of a plot twist, my name is Nick Hines, and I am not from Oasis. I'm actually the founder of Enshrine Computing. I left Oasis recently, but I will still be giving the talk on Oasis. But anyway, this actual talk is, I assume you can all see my screen, is about practical, secure, decentralized computing, a platform perspective. And the platform in this case is Oasis. So the reason why the talk is like this is because
we can't see, we just see it's loading still.
Okay, well, let's try that again. Share screen. And let me try sharing my entire screen this time. Maybe that will work better. You see my screen now?
It still says has started screen sharing, but we don't see it.
It says I'm sharing my entire screen. I see it.
Yeah, it looks blank for me too.
See, now how do you even deal with that? Okay, let me try to change browsers. Sorry, everyone, that's really weird. You never expect this to happen. Okay. Guess we'll try that again. Start with that. Zoom. Anyway, this is in Brave browser, so if it doesn't work, then, well, I guess it just wasn't meant to be.
Looks good.
Okay. Okay, now it works.
Works now.
Okay.
Yes.
Fantastic. Okay. Okay, so yeah, so as I was saying, this is a platform perspective. This is going to be about the lessons that we've learned operating a layer 1 compute network and a privacy layer, and just overall how we're approaching the space going forward. All right, so this is motivated a lot by the discussions that we've seen yesterday about how a lot of the focus on SGX and trust execution environments are practical concerns, layering, defense, and depth, and that's really where this talk is going to go. So the overall theme is just everything's really hard. Even when you're working in this zero trust environment, privacy is really hard. Figuring out what privacy even is hard. Getting people to pay for privacy is hard. Explain that TEE is not ZK, and it's not going to eat your laundry. It's not going to like to put your soul into like a really bad place is hard. Side channels, of course, are hard. And Miller is going to talk about that. And making easy to use, also hard. But there's one redeeming factor, and that is watching the privacy space grow every year as we see at these conferences and all of the overall adoption of privacy. That's easy. And that makes the rest of it easy. All right, so the outline of this talk is what we've done, and we built the stack, ending with Oasis privacy layer and starting with the Oasis network. And overall, these are what if the network were made of T's, what if the EVM were in a T, and finally, the Oasis privacy layer is what if smart contracts themselves were T's. And I'll talk about how it's been going, and then what's next, which is what if smart contracts could spawn T's. That's the overview of the talk. So now on to what we tried. So the first one is the Oasis network. This is the network that started. All of the Oasis network is essentially a scalability architecture that allows you to create custom replicated Intel SGX having runtime. So these are just blockchain layer 1s. Oasis network is kind of like a layer 0 that allows you to create T-enabled blockchain layer 1s. All right, so now on that network, we created, well, the Oasis Sapphire network. It's just confidential EVM. You put EVM inside of a trust execution environment, and that gives you private variables that are actually private and protected by the TE. Encryption data is the Merkle tree values are decrypted, consumed within the enclave, written back using encryption. And then it gives you an identical user experience to Ethereum, pretty close developer experience. You can use Hardhat and MetaMask and all those nice things, low fees. And then you can do built-in functions like RNGs, signing encryption, really interesting primitives, especially if you're doing like end-to-end encryption inside of contracts for like gas relaying. It's kind of interesting. And of course, you have general purpose smart contract support, and you can compose it with anything else. So you have really a protocol that supports protocols that involve private data. And the idea behind Sapphire is that there's no reason not to use it. So if it has all these nice properties and it's compatible with all of your EVM tooling, why wouldn't you use it? And the reason why you wouldn't, there actually is a reason why you wouldn't use it, and it's because you're already using another network. So you're already on Ethereum or Polygon, and like, why would you bother using another network? Privacy isn't so important. Who cares? All right, so that's why we have the Oasis privacy layer for Web3. And if you recall from the earlier slides, we have that the privacy layer for Web3 is as though smart contracts themselves have enclaves. So the way this works, I'll go to the next slide really fast, is that the user has a dApp. They submit transactions to their home network, which we're going to call Ethereum, and that's going to create some message that it's going to send over one of these newer message passing bridges to another blockchain network. In this case, it's the Sapphire network, holding the logic and secrets of the overall system. So this Sapphire network contract is, in essence, a software-defined enclave. So this is just like the primitive offered by SGX or Nitro enclaves. You post messages from the home network, like Ethereum, into the enclave on the Sapphire network. That smart contract written in Solidity will do some stuff and maybe get interacted with by the user. And then the outputs are then passed back over this message passing bridge, I guess you can also consider an RPC interface. And it goes back onto the host or home network where the actions are executed. So in a more concrete example, you have a DAO. You want to do secret ballot because, of course, you don't want vote retaliation. You don't want people anchoring the vote. And just overall, it's better when people don't know what other people are voting for. So what you do is you create the ballot in the home network on the DAO. You're going to have some termination conditions. It's going to, when it's finished, transfer a fat check to some destination wallet. So now that's going to be notarized, sent over to message passing bridge to the ballot collector dApp on the Sapphire network. So the ballot collector dApp is just basically a counter with some side channel resistance. I'll get into that in a bit. And it's just going to take messages from users containing their private vote and tally them up. Now, at the very end, once the termination conditions have been met, the final result will be tallied and sent back over to the home network. The votes remain private on Sapphire forever, or at least some definition of forever up to how long it takes for symmetric encryption to be broken. But hopefully we'll all be dead by then. But anyway, moving back to the previous slide, and the reason why we care about Oasis privacy layer in this workflow is that you can add confidentiality to dApps on existing networks because that's where the users already are. So you have the users on their home chain, the host chain, and the logic live on the Sapphire Enclave smart contract. And this is actually really useful for things like secret ballot, auctions, games, identity, and private payments. And it should be pretty easy to use. We're trying to make it so that you don't even need to know Oasis Sapphire exists. So this is the Oasis privacy layer, and it's just adding privacy to other Web3 applications. All right, so now how is this going? The biggest issue is the UX of privacy. And a lot of the issues around that are like usability versus security. So are you a developer or a user? And how do you value your own time and effort versus the value you're getting from security? Is that value even evident? How soon is it evident? And then if you're a developer, how do you deal with side channels and their mitigations? So one thing I like to think about constant resource algorithms is that they take one single amount of the resource, and that amount is a lot, which can be unfortunate for dApps that need performance or like to market themselves as being fast and cheap to use. And then, of course, you have this more insidious and fundamental issue of how do people even come to agree on what privacy even means in their particular context? So these are the overall topics questions that we're trying to ask and answer, and will allow us to create a more valuable network for people to use that actually provides usable privacy. So on the first topic of security versus usability, one thing that we had to walk back was this side channel resistance of not giving people the error codes of their transaction message. So you come in with a very hardliner philosophy thinking, hey, I don't want anyone to see the outputs, like no side effects, everything's gonna be private by default. And then you get some developers pop up saying, oh, hey, I can't debug my app, what do I do? And then you think, oh, gee, they probably want error messages. And I mean, like all side channels, you can just defer that to the application layer. Like the application developer will certainly figure it out. And like whether they figure it out or not, like that's really up to them, hard to know. But in the end, they do actually appreciate being able to debug their dApp. So there goes that little bit of security by default. And this isn't the only thing that we've had to walk back, like based on the very practical considerations of deploying this to users. We've had to also walk back unencrypted transactions being rejected. So now it's like 100% Ethereum compatible if you accidentally send all your secrets in plain text, like, I mean, I guess that's on you. I mean, you can always mitigate it, but the default behavior is that everything's allowed, and that's just for usability. Gas estimation is now enabled. Before it was disabled because that's like a very trivial side channel. Well, it makes it very trivial to exploit side channels. So that's enabled again because otherwise too many tools break. And then the biggest thing that we've had to walk back is that people actually want to use privacy layer ones. And I think that was a very interesting hypothesis like 3 or 4 years ago. But like really what we were finding is that people actually just want to use like their favorite networks with all the liquidity and all the memes and NFTs, and yeah, they just want to pump their bag. So basically if you're a privacy chain, you have to like really come at it with an approach of like, you want to help these people pump their bags. So I mean, it's like debatable whether that's really like a fundamentally ethical thing, but I mean that's just really what people are looking for these days. All right, so now some examples on just overall challenges with it, like the other things like side channels and adoption and standardization. So as you'll hear in the next talk about side channels, very likely, you have this ERC20 token problem where if you don't do anything and you just deploy it, it's going to be really leaky because it's by design leaky. If you just port it by itself, then an angry Andrew Miller is going to pop up on Twitter and chastise you for having side channels, and he'll add some spicy print lints to demonstrate it, and then your DApp will be crushed into dust, never to have high TVL again. But then, of course, the solution, which is ORAM, still needs some work, and I'm going to get into that right now. So here's 3 different ways that I'm thinking that we're approaching this Oblivious interface. So one is the Solidity Oblivious map library, where it basically implements either in Solidity or as a precompile a key value store that is oblivious. So you can do things like balances that's set and get, and it's all happy and oblivious. But of course, what do you do if you need to initialize ORAM over several transactions because the initialization is blowing out the gas limit? What happens if you forget to do this? How big should the ORAM be? And then what if it's too small? And for instance, needing multiple shards, what if it just runs out? Like, is it completely broken? And then what if transactions are too expensive because it's ORAM? Another thing you can do is a stateful precompile, where in the constructor, you just set a flag in the runtime that says this contract is oblivious. So now you have some of the similar problems as before, like how do you initialize it? How big should it be? But now you have this extra concern of why is get total supply slow? And you're wondering like, oh, this is completely public. Why does it matter? It's because now everything is oblivious and you have to pay that cost. And of course, there's also a Solidity pragma that you can do, but then you have the exact same problems before, but how do you distribute and maintain a custom compiler? Within the Solidity ecosystem, like not really that obvious. So like there are a lot of challenges here. And of course, if you do oblivious everything, then you're just like, you can just put it in the platform layer, no one thinks about it, but then it's super slow. So it's a really challenging trade-off to make. And then you have similar things happening in ERC 721, where you just have too many open questions, like which part of the 721 is private? Is it ownership? Is it the key? Is it the URL? And then what are the privacy guarantees? Are you looking for privacy from other users? Are you looking for privacy from the node operators? And it's really hard to know because each of these comes with its own special implementation, and it's hard to develop a standard around it. You can't even dictate the standard by fiat, it's hard to even know what kind of privacy people will like. And really what you end up having is this privacy manifold where you can pick any point in the space and it'll give you different privacy guarantees that are all perfectly acceptable for some particular use case, but maybe not yours. And so the overall, we really are just waiting for standards to emerge organically from the community, since privacy is not a one-size-fits-all solution, but on-chain secret management remains a useful tool, as I'll get to, and the final section of this presentation. So what's next? So the way I see it is that blockchain can be used as a trust layer for TEE. So blockchain provides the transparency and auditability that around the attestation and use of keys and TEEs, and it gives you a way to detect TEE misuse before it can get out of hand. So imagine if you had attestations just streaming through, you could have an AI algorithm just stop it, and then it's all good. So you can see the data coming out in a unexpected way and then stop it. So decentralized key management is still useful for autonomous dApps, and then sometimes you really do need a trusted third party. But then beyond that, having these really secure, like oblivious, hardened algorithms on chain, don't put on more armor, just move somewhere nicer. So that's where I'm thinking in my newest project, which is it's called Esrin. It's a secure decentralized computing network. And basically the idea is it's a Web3 first computing network where you have enclaved off-chain workloads, could be jobs, could be deployments, if we're using Kubernetes terminology. You trigger jobs, you use a variety of policies on-chain and off-chain, prove them within the enclave, trade the proofs of doing the policy correctly to decentralized secret keeping networks, and then use those to do computation over encrypted data. So now this is really just a framework, and I think it plays very nicely with a lot of the new developments we're seeing in the space. For instance, those really cool SGX, the new Lake processors that have like the AI machine learning models inside of SGX, then also NVIDIA confidential GPUs. So overall, just having more flexibility is really valuable. So the key component of this is that you move the algorithm and data to a TEE that both you trust and matches the workload. So this is really, instead of making the TEE super secure, acknowledging that the rest of the world exists and try to leverage some of the trust that already exists in the world. For example, a TEE running in Europe can benefit from GDPR, but then you need to do some interesting extended validation of the actual the enclave to make sure that's actually in the EU. So now that's an interesting problem, and that's what this work is trying to solve. And right now it's being used as a game for trout breeding. NFT secret seeds, completely autonomous. Trout have real identities. It's kind of fun. And then the benefits, the reason why we're doing this versus anything else that's trust, it's new in the space because it's trust minimizing, modular, plays well with other tools and technologies, respects people's privacy preferences, and really goes to them and their needs. Web3 first, rather than being Web2 and targeting people who don't really understand privacy or like the value of it. And then of course, not really a network, and it's not really decentralized. It's actually decentralizable, but that's really all you need with TE, as we're hearing in these talks. So that is my entire presentation. I appreciate the time for listening to it, and I welcome any questions that you may have.
Thank you so much, Nick. Questions for Nick? So I think while you are thinking of questions, let me ask one. So you mentioned that you can use OSS as a privacy layer for any any other blockchain. So in effect, if the OSS layer is storing secrets, so where does the execution happen? So does it necessitate that everything happens in the OSS layer now because it holds everything or all of the data, or at least most of the data?
Yes, right. So the idea with the privacy layer is that the data is held privately on Oasis Sapphire. So you're able to do the computation directly on-chain using the on-chain T and then bridge the results back over. And yeah, it is holding most of the data.
Then I'm curious. So what is the other home network doing versus, so what is the split of responsibilities between the two layers?
Yes, and that's the challenge of splitting any dApp into trusted, untrusted components. So the home dApp is like the DAO. So you have a DAO, it's doing all of the DAO maintenance, the overall membership, voting token, governance, all that, and just the voting happens on Sapphire. So all of the data pertaining to the votes and like some metadata is held on Sapphire. So the pith of the ballot is on Sapphire. So in that case, in that sense, most of the data is on Sapphire, but like the bulk of the non-private data, like all the rest of the stuff, exists on the home network without privacy. But then, of course, it depends on the application, because games necessarily use more privacy because, I mean, it's better for the game if privacy compounds the longer it's in the enclave, right? So games do more data on Sapphire side, but DAOs do more data on the enclave side, on the home network side.
I see. So I have one more question along similar lines. So I think you mentioned the importance of ORAMs, and as someone who's worked on ORAMs a lot, I think I'm intrigued at the connection. So I'm figuring out, if we compare this with just cloud computing in the absence of blockchains versus this world, when in both cases where TEs are involved. So why is it that ORAMs are more of an important problem over here than in other spaces? Is it the case that there are any parties can run nodes? I can just run a node on my blockchain network and still need to support the privacy mechanism, versus if it were to be, all of the nodes were to be deployed on the cloud like in AWS or Azure? Is that the difference why ORAMs are so important?
Yeah, totally. So, I mean, like the step one of protecting your secrets is not to give them to your enemy. But I guess like in the case of public blockchain, you can't really avoid that too much. So yeah, these sorts of mitigations are more necessary in blockchain just because of the adversarial nature of it.
Okay. So Aniket, you have a question?
Yeah, so my question actually start from Karthik's first question is that so we talked about this like other network and the OSS, right? So in terms of bridging there, what's the approach that you are looking to like because there could be significant nuances based on the which chain is on the other side that you're collecting data from. So what's your plan or how do you do bridging there?
Right, that's actually another good question because the way we do bridging right now is using state guardian network type bridges. So Stellar Bridge is the one specifically. We also have multi-chain bridge. Those are both state guardian. However, what we really want to get to is this zero knowledge bridge, which are basically coming out. You have like light clients, zero knowledge proofs, and then messages bridged across. So getting there would reduce that trust component. So like right now, it's closer to a separate network doing this bridging. But if we get to the zero knowledge place, it's much closer to the RPC protocol as we would be familiar with moving data into and out of an enclave, like on a bare metal system.
All right, thank you.
Thanks.
More questions? All right. If not, thanks a lot, Nick, for the interesting talk. Andrew, do you want to share your screen?
Yeah, sure. All right, you look okay?
Yes.
Okay.
So we are now seeing your slideshow. All right. Our next talk is by Andrew Miller. He's a faculty at UIUC, and he's going to talk to us about pitfalls and opportunities in DE-based smart contracts. Over to you, Andrew.
All right, perfect, fantastic. Yeah, so I will carry right on elaborating on some of the pitfalls around side channels and what's involved in getting security out of TE-based smart contracts, especially. Listening to the incredible talks yesterday and Nick's today already, you know, one of the things that stood out to me is that there's quite a lot of different use cases of TEs even within blockchain. So I mean, I've been coming at it from this viewpoint of private smart contracts, especially. One of the things that these categories don't break down all of that well, but I think of the needs of consensus, like I think we talked several talks yesterday, is fairly different than the needs for private smart contracts. There's a bunch of other applications too that do some, they're not the blockchain and they're not the contracts on the blockchain, but there's some, you know, private transaction lookup service that helps the blockchain. That's how I think of this mobile coin, you know, Fog project as well. There's some things in the middle, like Fala is really interesting because it implements smart contracts, but it aims at middleware kind of tasks. And I think this, you know, if you have like a bridge kind of in the loop, the way Nick describes, like with the Oasis privacy layer is that's, you know, maybe in between. And then there's a bunch of, you know, so the Flashbots, you know, block space auction, you know, basically carried out in SGX isn't exactly one of the others, but kind of overlaps a bit. So, you know, there's quite a lot of these. So even this, you know, this space is even bigger. We've only got a incomplete sampling of it, even from all of the talks on this. So there's a lot more to go. I'm going to come back to this point a little bit later, but I think these all fundamentally have some needs in common that define a blockchain TEE use case that's distinct from the cloud use case that's kind of predominant. So, you know, I want to come back to that. But I'm just going to talk about the smart contracts viewpoint today. And the way that I think of the progression towards this is that you need to understand TEEs if you're a smart contract developer and want to know, you know, you're probably, if you're a smart contract developer, already learning what zero knowledge is today. You learned about commit and reveal and consensus earlier. For a sufficiently complicated smart contract goal, especially if you have strong privacy goals when you're writing your smart contract, which is a new thing to think about as a smart contract dev. But if you're starting on the ZK direction, then you'll come up to these privacy goals eventually. You eventually need to turn to something either multi-party based or trusted hardware based, or possibly both, which is, you know, an extra assumption, but you need it to handle some applications. And so this is why this is an important, you know, tool in the toolbox to develop. Motivating examples are important. I think an auction example is a sufficient motivation for why you can't do everything with zero knowledge proofs and commitments. You need multi-party or trusted hardware enclaves if you want to tackle this application and if you care about strong privacy. If you don't care about privacy in the full sense, then you can get away with like commit and reveal or commit and snark proof. But if you want to be able to have an auction where no one, not the auctioneer, sees all of the bids together, not even after the fact, like maybe the winner knows what they paid, but no one else needs to know what the other losing bids were, because those are like pent up, unsatisfied demand that probably leaks over into the next epoch or whatever. You can't just do that using zero knowledge proofs alone. You kind of get up against this wall and then need to take on the MPC or the TEE approach to get past that. So smart contract developers eventually need this. I think this is why this is such an important area to work in. And I'll just briefly tease my new venture, Honey Badger Cooperation Lab, is about building a credit network application that's privacy preserving, and that's the application that we want to build. Even though I'm going to talk about side channels mostly, I just want you to know that my viewpoint is coming at this as there's work to do, but it's ultimately optimistic. So you can decide I'm unhinged at the end of this afterward, but that's how it goes. So I'll get into the high level description, and then I'll tell a couple of stories on these side channel vulnerability disclosures we've done recently. So at a high level, the smart contract setting is that we have a blockchain. I think of that as possibly built using enclaves, but conceptually separate from the enclave. It's just a plain text public blockchain. But that blockchain will store encrypted transactions, and users send their transactions encrypted now, such that only enclaves can compute on the encrypted transactions. And like any, the enclave is just the processor. It's part of a computer system that includes the disk and the RAM, which is said to be outside of the trusted portion of the system. So practically, this involves computing on encrypted data that's stored in a local database. And so we'll come back to a couple of these concepts in a little more detail as we go. So I kind of mentioned by my categories there, but for this work, we basically considered a cohort of 4 smart contract platforms that all use TEs, and not exactly the same way, but fairly close. And of these, Oasis and Secret have a mainnet launch. Phala and Obscuro are still doing test network, or still doing development, but they have public test networks. So these are kind of all the code bases and public instances that we could go in and look at. So the first story that I want to tell is what goes into the sgx.fail paper. It's a fun website. You can look into it. My part in this only has to do with Secret Network. The rest of the scope of sgx.fail is, much broader, especially affecting like 4K DVD rips is, what's at stake of it. But really the issue is about TCB recovery and what it takes to be responsive to TCB recovery. So the kind of architecture detail that plays a big role in this is the idea of, where are the keys in the enclaves? How's that arranged? So what Secret Network and Obscuro so far do, but not Phala and Oasis, I'll get to that in a moment. But what they do is that they have a single master secret key that's the decryption key for the entire universe of smart contracts and transactions. And this key is replicated in the sense that any SGX enclave of suitable version numbers and updates and all that joins the network is entitled to get a copy just in the enclave of that secret key. And then the public key for that secret key is, well known. That's on the blockchain. So, that's the public key to which users encrypt their transactions, so that only the enclaves with the master secret key can decrypt them. Now, the issue with this is that it prevents a really large attack surface. And, the nature of how we got to this was that the attack surface has kind of been easy to, this is really like a difference between the way things are presented in side channels papers like Cash Out and LVI in the past that say, okay, this is completely broken, but maybe the demo isn't quite weaponized, to make it where it's clear. So, even when Secret Network launched, this is like their documentation in gray paper. They kind of, encourage people to think of SGX side channels as theoretical attacks that typically, require expensive equipment, or they go into side channels research labs. Even in 2020, when this comment was made, this was a little bit, blind to the history, because like the demos for Cash Out and LVI, for example, were fairly potent, even if not flat out weaponized. So, even at the time, this was kind of not the right judgment. Anyway, so Apic Leak was the most recent instance of a worst case vulnerability for SGX. Worst case meaning it's like easy to exploit with just software, and the scope of it is quite large. Like you could get out the attestation keys themselves, which means you can join the network with a completely fake node. So this was publicly announced in August, but that had been like a long 9-month embargo process from the researchers who had first found it. And so when it was published, there were microcode updates and patches, right available. But on the Intel Attestation Service website, it's kind of, I found the language as a somewhat newcomer to SGX kind of hard to decode. So mentioned a TCB recovery was scheduled. I had to go dig into what that means and found it a little confusing. Frankly, I think of TCB recovery as almost a dog whistle phrase. It's something that, means something specific to sysadmins who are already like patching SGX-based systems, but it's not so meaningful that it spooks application developers or users. So, the patches are available, but the TCB recovery is not scheduled till later. TCB recovery basically is when the attestation service will bounce you if you haven't upgraded your BIOS to the new version. But the message of the SGX fail, paper and discussion on it is that this is a process fraught with difficult trade-offs, because you don't want to knock out users who, now their product doesn't work. They can't play the DVDs that they were expecting. So this is a very tough thing to manage. And back how the story goes. So when we started looking at this in October, I think the SGX fail, the rest of the team had been looking at it earlier, but this is when I got around to it. Couldn't find any discussion about how Secret Network had handled APIC leak. What I understand now is that they basically had done a kind of analysis of the processors that can get on the Secret Network and that were vulnerable to APIC leak, and they determined that there was no intersection. I didn't even understand some of the documentation that, or some of the terminology that, anyway, I might have realized this, but I didn't realize some details, so I thought this would be easier than maybe an informed person might have, but I turned out to get lucky just doing Best Buy shopping, find a PC that's capable of both joining the network and vulnerable to APIC, and that was kind of, what it takes to get the master keys out. So once we showed them, okay, we found machines that can do this, they immediately turned off the registration of new nodes to the network, which is a great mitigation because it stops anyone tipped off by this from being able to join the network. And then they refined their ability to basically filter out potentially vulnerable hardware and, kick them from the network. But, that was the couple of months of time from the public, let alone private knowledge of it before that was, fixed down. And of course, again, because of the large attack surface, we could just show up with the node that we bought and get the, the whole keys. So, you can contrast this with what the Akita research paper says and what Oasis and Fowler practically do already, which is this idea of compartmentalization, which is taking on some centralization trade-off, where you say, well, we'll have key manager nodes that are in small number, and you either have to be trusted or have a lot of stake to be a key manager node. And ideally, they don't even have the master key in plain text. The master key only within the enclave. They'd only have shares of a master key, never reconstituted on one enclave even at the same time. The idea is that there's maybe a larger number of worker nodes that process one contract at a time, and they only get contract-specific keys rather than like all of the keys together. So this basically produces a much harder to attack surface, at least from an outsider, even though it's not a perfect solution. On the other hand, this has a lot of trade-offs, which is why Secret Network, is not opting for this approach right now, which is that it's harder to, it creates barriers to entry for RPC nodes, makes some other things are a downside for this, but this is what it looks like to basically reduce your attack surface so that, basically the question is, if we don't, if we leave the same attack surface, we could just say, well, now APIC leak is over, maybe the worst side channels are behind us. The pattern is like every year, someone named Daniel G, there's like two of them, and they like take turns finding the next side channel attack on SGX is how I think of it. Who knows if they're behind us or if they're going to happen. And so it's basically a tough choice to make. I'll move it kind of quickly to finish through the rest. And I'm not going to give all the details about this. So the follow-up that we did on this is about, we call it SGX exonerated because it's about privacy leaks and side channels that don't involve any failure of the TE itself. It's just the, design of the blockchain system around it. So you can read our paper online about this. I'm not going to present all of it to leave some goodies for students. I think some on this call, like Nirla and Yunchi, and may present later. So be on the lookout for presentations about the rest of these. But I'll just basically cover the spicy printf version of this because we've already described it a bunch. And it's the most important because it's still ongoing. And actually I'll go quick through this because Nick did a great job of kind of pointing out the detail. But I'll just show what this, storage interface looks like. So if you do smart contracts, smart contracts have persistent storage, like a key value store for, this is what a Solidity ERC20 code looks like. It modifies the account balances to carry out a transfer. That's cool. So what it looks like when you run this in Secret or Oasis is that when you are processing a transfer, the first thing you do is get the current balance of the sender. That turns into a fetch of an encrypted key that's going to return an encrypted value. So you're using the untrusted storage to store ciphertext keys and ciphertext values. And so you say get the encrypted value, it returns the encrypted value, the enclave decrypts it, that's how you get the current balance. Now it's time to deduct the sender's balance, so we send a set with new encrypted value, but critically the exact same key, because that's how the encrypted value store is working. It's got encrypted keys, but you fetch with the same key that you previously stored for. So, maybe you can see where this is going. So a spicy printf is when you modify the untrusted portion of the code base. We can't modify the enclave, that's signed and kind of fixed to the network, but we can modify the Go code that's sitting around the enclave. Right, you can modify the untrusted operating system without having to code sign or get an attestation. So you simply add a log at that boundary of the storage interface in the enclave, and a sample of what you get from that is then pretty concerning from a transaction metadata point of view. Like you get a sequence of encrypted, these are the ciphertexts of the keys in the key value store, and so this is the access channel debug trace, and what it has is that the receiver's account key, this isn't the address of the receiver's account, but it's the encrypted key corresponding to the record that stores their balance. And so that's always in the same location each time. So you can, end this sender receiver, you get full linking basically. So as Nick alluded to, this is, an kind of unresolvable, at least for the near term thing, because and what Secret Network is doing going forward is basically building a new contract standard for tokens that basically add Monero-like decoys or obfuscations into it. The kind of comprehensive solution, this would involve oblivious RAM, but we would need kind of oblivious RAM in a highly concurrent and say, query-friendly structure that's different than what we have right now. And then Nick did a great job of explaining, that it's not obvious how to expose this to contract developers. You don't want to automatically ORAM everything. That would be very slow. One big ORAM is kind of less convenient than small ORAMs, but this is complexity to the app developer. And so, I think this documentation is totally accurate and, reasonable now. It's a good response, to acknowledge it like this, that, the obfuscation will be sort of partial. I think that we go down this path though, and we're going to basically have a cat and mouse game of how easy it is to do access pattern leakage. It's really the same. This is an allusion to, Paul Grubbs and the cycle of improved encrypted databases versus, more powerful ways of exploiting the statistical leakage that obfuscation gives you. So it's tough, but how to add oblivious RAM to smart contracts for this setting is an open challenge. It's the same thing in Oasis. So, for Secret, the trouble is that these things are already in use, have been in use for a while, and likely expected privacy. For Oasis, such tokens aren't there yet, but we got a warning added to make it clear that you can't just port ERC20 and you get a transaction metadata hiding system. It's more complicated than that. In the sake of time, I will completely skip the issue on updated transparency, and I only had a teaser slide for this anyway. So, the other bit of the story and the really hard part, the students on this paper did all the work of making a cool demonstration and fully derive it. But basically, Secret was launched without the rollback actions that I think were heard in every single one of the talks from yesterday. It's kind of taken for granted in the research world that the rollback attacks are necessary, but Secret launched without the rollback attacks or proofs of publication present. And so the rest of this SG exonerated paper is really about how we showed that these actually are real rather than theoretical attacks, and they affect, all of the SNP20 tokens in use today, basically. This has been patched, so they have now added a proof of publication. So, this line was kind of the more simple spot the vulnerability and close the gap than the previous ones. Okay, so my guess is that I have like 2 minutes or something, so let me just switch to this anyway. So those were storytelling. I want to try to zoom out and give some useful insights to you all. Coming back to this idea of disintermediation, one thing that I think is really interesting is the difference in requirements between this like Suave Flashbox MEV auction case and what I kind of started from, which is just smart contracts. So the thing with the auction is that, you know, Suave only needs SGX to work to keep things secret on this kind of rapid thing. You know, they really need it private for the duration of the auction and then disclose it afterwards. It no longer matters. So to break the desired privacy goals, you need an attack that works instantaneously. Unfortunately, the APIC leak style vulnerability, if one of those could be exploited again to get the attestation key itself out so that you can join a fake enclave to the network and pretend it's an enclave that's sealed off, that would be a problem. But side channels that are a little bit slower, even like the ones that we were, you know, demoing using rollback attacks, being a little bit slower makes it, you know, harder to attack there. So there's a temporal component that's bad for long-term privacy goal like we want in the private smart contracts, but is somewhat easier for just the auction case. On the other hand, it's hard to monetize a privacy break, whereas the, you know, greed component of being able to fight over the millions of dollars of MEV, you know, it's much more highly monetizable. So to me, this suggests one of the ways to work together is to try to promote, you know, bug bounties and challenge networks that are basically designed to be broken, like early warning canaries, you know, that are hopefully easy to monetize if you disclose the vulnerability that you find, but are really, you know, tempting to side channel people to, you know, go attack that way. That's just a concept there. The last point that I want to talk about is something that's really just kind of formed, you know, in some clarity to me, but now I think this is like a really big deal, is that there's a very big difference between what the enterprise and typical cloud use cases and what we want for all of those blockchain operations. So in the cloud case, typically what you have is there's the cloud operator, you don't want to trust those, but then there's the owner of the virtual machine or the application developer who is paying the cloud, who's the cloud's customer. And we think of attestation, yeah, let's just look at it here. We think of attestation as how the cloud or the host of the VM convinces the relying party, meaning the VM owner or the application developer whose account it is, you know, they don't have to trust the cloud. The app developer doesn't have to trust the cloud. That's the enterprise use case. What we care about in the blockchain case is that the developer and the cloud, both you shouldn't have to trust. The relying party is the users who should be able to see the attestations, but they shouldn't have to touch either the developer, trust either the developer or the cloud. But, and this, you know, kind of came up in some yesterday talks too, there's different notions of attestation. This is actually like a distinguishing factor of attestation that SGX kind of supports this blockchain use case. While as far as I can tell, all of TDX, the NVIDIA thing, SEV, all of them are geared towards this enterprise use case and can't, at least not without coming up with some workaround or some change, you know, don't directly support this publicly checkable remote attestation use case. So, you know, I went and listened to all of these talks on 1.5x speed from the Open Confidential Computing Conference just a little bit ago. And I was trying to listen to see if I could catch any, you know, coded phrases that mean one thing to another. I spotted one instance of, like, I think the Azure CTO saying, okay, here's a case with autonomous vehicle data. Maybe you don't want to trust the application owner or the cloud. So, you know, maybe there's like a cognitive foothold into the enterprise requirements list driving world that we could insert ourselves as people with blockchain use cases. So I'll just wrap up, you know, recapping, but what I think are the, you know, open challenges and I think low-hanging fruit opportunities. I think it's clear that there are some best practices and ideas that are, you know, just below the surface, but I think we can get to the nuance and understanding of these. I think all of these different projects should be carefully looking at the design choices that each other make. You know, we have this kind of security call-out culture in smart contract code anyway, so I think that that's the appropriate thing to bring here. Things that are kind of common features that we all need, like reproducible builds and, you know, transferable remote attestation, those might be solvable for all of us together. I really think we should be finding a way to have a blockchain seat at the table with all the hardware companies. I think that that's not the case now, but could be an easy thing to improve. I mentioned the bug bounties. Yeah, and I mean, Nick did a great job of explaining the kind of challenges and where, you know, oblivious RAM and data structures can go. Kartik, you know, if this is where the oblivious data structures need to be inserted into, basically. So I hope we get oblivious kind of takes over all the smart contract devs mindshare the way that ZK does today. And, you know, I'm not a hardware guy, so I don't even know if there's any, you know, path forward on this, but I like the idea of threatening to compete with the existing hardware developer companies by building blockchain native, maybe simpler use case TEs that just say do oblivious execution of an EVM. Maybe that's something within range of a mining company that can't build mining equipment anymore. Maybe they could go into this for us. So I will stop it there. Would love to take any questions, and thank you all.
Thanks a lot, Andrew. Questions? While someone is thinking about, go ahead.
Yeah, maybe let me get started with something. So this compartmentalization that you mentioned, where the smart contracts get their own keys, right? So it seems like a very good use case for identity-based cryptography kind of thing, where smart contract IDs are basically their code or some kind of thing. Don't know, probably seems like something which is canonical, so already thought about, but it came to me, so that I thought I'll mention.
Yeah, definitely. I bet there's a lot of interesting ideas like that. I mean, what Akita and Oasis do for this is somewhat simple. It's a lot like hierarchical key derivation like you see in a wallet. So, I mean, there's just like a derived secret key from a master secret key and a derived public key from a master public key. So it's fairly simple what this requires. Yeah, something like IVE could be really interesting where you could send to a contract that hasn't been initialized yet or something. Yeah, very possible.
Yeah, where you don't need to even know that before. That's the advantage of IBE over the basic public key-based approach that you mentioned.
Yeah. I think that there is a ton of, so what I think has happened is that the negative sentiment towards SGX has reached like a trough mimetic level to the extent that it's overcorrected and a little irrational. And so, people, I think security-minded people who otherwise might be doing really cool cryptography plus TEE, they kind of get turned away from it just at the kind of top level concern about the trust model. I have to trust Intel, there's side channels. But I think that there's a ton of kind of interesting ideas, low-hanging fruit, productive design space at this kind of, combination of them. So I would really encourage people to, try mashing up some cryptography and TEEs. It's not like you use crypto or you use TEEs. Every interesting system uses a non-trivial combination of them all.
Yeah, so I want to just finish on that topic. It can be nice because you have worked on MPC as well as you're looking into TA in detail. How would you compare if, what's the, can you characterize that these are the use cases where one will be better or other?
It's tough. If you have a data access pattern, for example, like a large data set, you need oblivious RAM in your MPC the same way that you need oblivious RAM for the trusted hardware enclaves. Like that's not a difference. If anything, it's just that you might be more tempted to use a large data set with TEEs because in general, things go faster compared to MPC. Whereas in MPC, it's in my experience, it's so difficult to make something go fast. So I mean, our experience, I don't think we have this launched just yet, but you can, we have a blog post about it that covers it. It's under Honey Badger Swap. So I mean, the idea of combining multi-party computation with, blockchains as an alternate way of building a private auction is something that makes a lot of sense and we've worked on. The challenge with it is just very difficult to make it very performant. In my experience, it's a lot harder to program the multi-party computation than it is to program the smart contracts, especially for the trusted hardware enclaves. So we spent a bunch of time making this work for a kind of simple Uniswap, a private Uniswap dark pool, basically. But that's not offering transaction metadata privacy. It's actually just revealing. It has the same spicy printf problem. It doesn't try at all to hide who is interacting with the pool at the time. To do that, we would need to add ORAM, and this was just barely able to be sort of plausible. So I think a secure solution would involve both MPC and trusted hardware enclaves, because one thing the enclaves do a good job of is prevent you from hoarding on to the secret share data forever. So if you can handle the performance, then ideally the MPC nodes would also be running inside an enclave. I mean, that's essentially what this threshold key manager approach is. So I mean, everything else I think comes down to like ease of implementation and performance trade-offs. MPC combined with TEEs, though, is for sure an excellent direction.
Thanks.
Please go, Itai.
Yeah, great talk, Andrew. Thank you. I guess my interpretation of the ERC20 attack is that you're saying there's no ORAM solution, which is kind of horrible. I guess I wonder if there's maybe ways to change, instead of say using an ERC20, you can use a token that looks like Zcash, right? So you just write things on a nullifier. And so you're hiding kind of the access pattern and basically using SGX to actually do all the hard leveraging. So basically my question maybe is, maybe there's a path here related to building a different type of ORAM that will kind of use SGX or, TEs in general.
I mean, it's a super good point. Even if you have something like Secret Network with a smart contract system using SGX, there's nothing that says you have to use that for tokens. I think the ideal system should be you use ZK proofs for everything that you can with ZK proofs. So in my world, ideally, tech solution is like Zcash plus Secret Network, where you have Zcash for all of the tokens. Every application that's just token holding, you might as well use nullifiers and Zcash for that. And if you truly need this auction, then use that for SGX. But then the next APIC leak might only threaten the current state of some auction contracts, not the entire history of the auction and the entire history of all of the tokens on your platform. So yeah, we should definitely encourage the use of ZKP wisely wherever it fits, and SGX only when it's not more expedient to use one of the others. And like you say, maybe there's a way to kind of more conceptually have an ORAM that makes use of that. That's really interesting. I suspect that there's a lot of potential there.
Thanks, Andrew. More questions? So I actually have a comment. So I loved your slide number 2 with those 3 intersections and trying to synthesize all the problems, problems in this area. Yeah, so that one.
Good. Yeah, that was one of those fun slides made after all being inspired by all the talks yesterday. So yep.
So if there are no more questions, I think let's thank Andrew and move into the panel, because that is what we have scheduled next. So let me actually pin all the speakers and we can get started in a minute. All right. So again, our goal with the panel is to have interesting discussions and learn more about the space. So I actually want to start off with one question that we have discussed, one topic that we have discussed quite a bit today and not much yesterday, and that has been with respect to ORAMs and TEs. So I think I'm trying to get a sense of, so ORAMs, I think there has been a lot of research in the space for the last 2 or 3 decades, right? And I think there is a new application, so to speak, where we are considering ORAMs. So is the problem space over here any different from what it was earlier, or is it just the same problem that we're trying to solve, but trying to really make it work in this application?
I think the challenges are largely the same. I think just the question is really the motivation for it, and why would the people put in the expense of adding ORAM? It's really hard to monetize ORAM, so we don't really see it happening. And that's probably why we don't see it happening.
I mean, even more concretely, ORAM is typically portrayed in this kind of like that, simplistic enterprise cloudy setting where like you've got the client and they're the data owner and it's their data. I mean, so at a minimum, this would have to be like a heavily multi-client kind of ORAM. I mean, then it's a little different because the client is really not the users of the blockchain system, but actually just the enclave of the validator nodes executing the smart contract. So, arguably, even though it would be a multi-user purpose, maybe it's really only single client ORAM, but a little different. I mean, I think the most practical immediate problem is that both Oasis and Secret, you don't get a lot of use out of having API interfaces that are not just the consensus nodes that any user can go access. That's how you query your account balance from MetaMask or from Keplr. And so being able to support these kind of concurrent reads because they're served by independent API nodes, are they each going to run ORAM? You can't just like cause them all to publish your ORAM read requests in the blockchain to check your account balance. So I mean, that to me is the main thing that isn't served by existing ORAM notions. I suspect like formally there's definitional issues as well.
I see. That's helpful. So I'm going through this this list of questions over here on onlinequestions.org. So the next most sorry, go ahead, Itai.
Yeah, I just want to add to that because I guess this is related to my previous question. In a sense, like the regular traditional ORAM, right? You have a user and a malicious memory, right? And you somehow want to hide the access pattern from this malicious memory. And yeah, Andrew's correct that here we have, I guess, multiple users, so that's already one complication. But you can here even imagine the fact that you have these users that actually have their own TE, right? So there's this malicious memory, but there's also users that have their own TE, and that actually changes things quite a bit. So for example, you just take any copy and write data structure. So basically a data structure that you only write, just extend the log. And all you do is just encrypt the content. Okay, maybe you have to be a little bit more careful, but roughly speaking, you encrypt kind of messages on the log, and then the clients will just feed this log and update their data structure internally. So that's kind of a trivial ORAM, right? So I can solve something much more trivial. Again, I have to be careful, right? That if you're there's maybe some sequence number inside, so that it's kind of completely pseudo-random. But here's a simple ORAM, right? That in this different model. So I guess one of the things that would be interesting is to understand exactly what the model is.
Aniket, please go ahead.
Yeah. So just to add on to that, this came up in some earlier discussion with Andrew himself. Like the concurrency is also an important issue. Many of the ORAMs were built. I mean, some of this problem is already thought through, but still having protocols which can allow the concurrent accesses, read and write could be relevant as well, right? Yeah, in terms of the something to require.
I think just since you're here, Kartik, and I'll just shill directly to you. Like the oblivious data structures is, I think, a really great thing to add. So I mean, we're kind of used to just the key value store. I mean, Solidity has like not even range iteration support, at least like Cosm Wasm does that. So it's they're already unstructured key value storages, but then SSD latency is the only bottleneck, so it's not been the top issue. Here, there's probably a really big benefit in doing something like what the Oblivion language does, where it picks maybe a suitable ORAM partitioning, or if there's a way to select, we'll have like graph structures that are more structured than RAM. So an oblivious data structure would give some performance benefit. If that could be exposed to smart contract developers somehow, it might be really good.
I see. All right, so I think let's move on to the next question. So it appears the next most sorted question is something that Arvind asked earlier today on chat as well. So Arvind, do you want to maybe ask a question?
Sure. So this is again a basic question. So yesterday we were talking about settings of homogeneous or heterogeneous, where do you assume like all the parties in a protocol have access to TEs, or some of them do and some of them don't? And at some point we were also talking about adding accountability to protocols with TEE could be one solution. So I was just wondering if you have a protocol where some parties are using TEEs, their messages that are coming out of them in the protocol, are they something that can be verified? Are they something that can be publicly verified? what I mean by that is that the messages that are coming out from a party that uses a TE, is there a way for others to verify that this guy is actually has executed the TE and that's what he's sending messages with?
I mean, I think in a nutshell, that's what the remote attestation offers. So I mean, with the caveat that it depends on all the assumptions, that the remote attestation system is not currently broken. But I mean, given that assumption, yeah, that's what remote attestation tries to offer. I mean, I would draw this distinction between what SGX offers, which is that the report you get from IIS or from the DCAP process is actually a certificate that can be checked non-interactively. In the case of SEV, it's like you have to make your own connection to it to do the attestation. There's not like a certificate you can get on a message that you can check. So to me, this is something that's like a feature that SGX has, but doesn't have a name for, and none of the others have because no one's asked for it yet.
I see.
Actually, Andrew, can I ask a follow-up question to that? So I think, could you create essentially an SEV quoting enclave to turn the interactive step into a non-interactive one?
Probably. That'd be cool. That'd be like hacking a feature into an enterprise system, like a proper classic hack a new feature into something. Yeah, maybe. Or like a TLS notary kind of thing, maybe.
Yeah, I think it'd be useful.
So just so that I understand, but this remote attestation can offer verifiability, but not public verifiability, right?
I mean, you get a certificate that has the output and the hash of the program enclave. And that certificate has a chain of trust, just like certificates, all the way up to Intel's well-known public signing key. Yeah, I see Mick raise a hand and maybe can ask you.
Yeah, sorry, I can. At some level, the real question I think for both SEV and SGX is what's your root of trust. At least in the case of SGX, we have a root of trust, which is what Andrew's talking about, that you can go back and verify the certificate to a shared root of trust. In this case, it's Intel's ability to assign the validity to the hardware for SGX. I think that would be the challenge of doing something with SEV is that what is that root of trust that allows you to do the non-interactive verification of the certificates? So the idea of third-party non-interactive verification is really that ability that I was talking about yesterday. I can ask you to perform a computation and then I can prove to Andrew that I did it, even though you have no access to any of the pieces of the computation, because we have that shared root of trust.
So along similar lines, so I think so if we're using, let's say, instead of just SGX, multiple cryptographic coprocessors like TPMs or Google Title, along with TEs, what is the best way to think about using a combination of these? We've spoken about using heterogeneity over here, but what is the best way of actually, what is one or a few use cases where a combination of these can be used?
Well, I know that LIT protocol is a secret sharing network that hosts the secret shares inside of SGX. So it's a kind of novel combination that's pretty good for data management use cases.
I think it's tough without a root of trust. I mean, if you could get remote attestation of such a good question. I don't really have any full form thoughts on this. So at the risk of just brainstorming out loud, I wonder if you can have you have a heterogeneous system with some trust zone deployments and an SEV and an Intel SGX. If only Intel SGX supports the non-interactive certificate, attestation, maybe it can do the interactive verification with all of the others. I don't know whether that's getting you defense in depth threading through all of them, or you're just getting the worst of them out of that. It's a great question.
So Mick, you also have a comment on chat. Do you want to maybe say it out aloud so that everyone can hear it?
Sorry, gotta unmute too many things. Yeah, and there is something that okay, so let me back up for a second. So we use the DLT in the private data objects work as the enclave registry. And so all the verification of the enclave attestations, so determining what constitutes a valid MR enclave, what constitutes a valid level of firmware, is all determined in the community defined DLT. So you can register an enclave, it has to go through all of the verification in a public way. So in some sense, we're using as a proxy for determining correctness from IAS or the DCAP certificates. My question is really, can you build a DLT that would serve something like that, that same purpose as the root of trust for verifying hardware integrity for a variety of different applications that way? I don't know. Right. I mean, this is a question for all of you to a certain degree, because there's a lot of complexities in here. But this is something we've been thinking about often, is what would it take to make a community-based verification that accepts input from the manufacturer, input from the hardware design company, but does not cede policy to those organizations? But I think there's an interesting question there. I don't know what the answer is.
Yeah, I think that's a great articulation of the goal that the blockchain community would absolutely want, to be able to make a root of trust that's somehow the community rather than any one hardware vendor. That's a great statement of the problem.
I guess a part of the challenge over here has got to do with, perhaps the different attacker models that exist with all of this hardware and different efficiency characteristics that you may get when we use some of these hardwares.
Yeah, and I'd like to add, I think, some thoughts on heterogeneity. I see it as both a curse and a blessing. So on the one hand, the big problem that we want to try to solve is a decorrelation, right? We don't want to have one type of failure, one type of zero-day attack break the whole system. So heterogeneity is a blessing because it can give a decorrelation of failure, and that's very important. Unfortunately, the other side of it is that heterogeneity can be a curse if different entities kind of provide you with different properties. So at least, in theoretical models, we like to have very clean, you're either honest or malicious. And here you kind of say, well, we can protect against these types of things, and this other hardware can protect against these other types of things, and this third one can protect against a third type. And so that kind of makes a much more, I guess, complicates the model of what you're trying to obtain. I think part of what needs to happen is that we need to embrace homogeneity and try to kind of, take more of the blessing and try to reduce the amount of curse. Because in the long term, it actually makes sense to be able to decentralize things, to decorrelate the failures, but provide kind of at least, these decorrelated failures do provide the same type of guarantees, at least are supposed to provide the same type of guarantees in the long run.
So are you suggesting that there has to be some sort of so in terms of the models that these different hardware processors provide you with, there has to be some sort of a relationship so that it's easier to design protocols? Is that what you're suggesting?
I mean, I think first we need to just have a language. Maybe I'm still new to this, so I don't even understand formally what does each different vendor provide and what it doesn't provide. And so I think first of all we need to have some sort of formal language that can describe the properties, and then when we have this language, we can say, okay, maybe we can, maybe it's a layers and we can build one on top of the other. Maybe some of these things should be standardized as a next phase.
I see. So, so along these lines, as well as the kind of discussions we had yesterday, I was mulling over it in the evening yesterday, and one of the topics or themes of yesterday's panel was let's not think of TEs as gives you an all or nothing, and somehow, at least from a theoretical standpoint, that is how I used to think of it. So and one of the things that we spoke about a lot was we should think of it as one of the mechanisms that gives you defense in depth, and we should think about TEs as giving you security, but not entirely, perhaps. So I was wondering if so in fact, even so Heidi mentioned this, there are these nice threat model, there's a nice threat model section in the paper, which makes sense, but at the end of it, it may or may not hold, right? So as a protocol designer, what is the best way for me to think about this? So if I'm not saying, okay, TEs give me guarantees XYZ, the other extreme I think of is it gives me nothing. Or is there something in between that I can write in my, let's say I'm writing my next paper to S&P and I'm writing my threat model. How is it that I can model a TE over there?
I mean, I'll just mention two kind of prior works that I think do some of that. So there's the paper Sealed Glass Proofs. I think Fan was on that. Other various folks were, where it's like essentially like a graceful degradation model. Like it kind of contemplates a world where an SGX may fail, but it may fail for privacy, but not for integrity. Yeah, you want to jump in, Fan?
Oh, sorry, I didn't mean to. I just please go ahead.
Oh, okay. Well, that's the end of what to say about that. The other paper that I would make a shout out to is researcher Ruja Lee. I think he's a postdoc at Birmingham right now, if I got the affiliations right. He had a survey of TE-based smart contracts in PET last year. So he's been doing some work on trying to make some formal model, in between there that I think is really interesting. I think that's a great, description of what's missing, is a better, articulation of what exactly our requirements and expectations are. And I would expect it to be in a way that's kind of nuanced, with like a couple of different models, or, some guarantees under this failure mode, a subset of the guarantees under another failure mode.
I can just add to that. So another line of thinking is maybe you can somehow detect the TE failures and design the protocol that can detect and handle TE failures. Privacy failures may be very hard to detect, but the integrity failures you may be able to detect. For example, if the integrity failure will translate into, denial of service, detect failures, but it's very specific to.
I finally lost you for like 10 seconds.
Oh, really? Sorry, I didn't know where you lost me. So I was saying there are specific applications, quite specific scenarios where maybe you can design the protocol so that the failures of TEs ends up with some detectable symptoms. I think it's specific to use cases, and we are thinking in some particular usage of this in anonymous broadcast, for example. So this is an ongoing work of with collaborators. But I wonder, right, how broad this idea can be applied to different scenarios.
More thoughts, or should we move on? Okay. So the next question is, what is the nearest alternative to using TEs in your project? So I think maybe each of you can go one person at a time. Andrew, do you want to start first?
Yeah, sure. I mean, the best alternative, I guess I did mention that in the last question, but I think the best alternative is MP speeds. Like you could do some MPC-based alternative. I think that then you are getting some, you're not threatened by APIC leak or whatever the successor is, but you can't say guarantee that people throw away their shares. So that's kind of the trade-off. So I think ideally you would have both. I think like Penumbra is a cool example of a project that's based on, you know, threshold homomorphic encryption for some specific applications and then tune for that. So it's not exactly a replacement for arbitrary smart contract execution, but I think that's a good example of the kind of a good way of kind of pushing the boundary of what you can do with threshold-based operations. I think that's the direction that you know, Secret's headed to with Secret 2.0, and so Sergey will talk about that later. So to me, threshold something or other is the only alternative. Once you get to a thing where you actually need it, then it's only hardware threshold, and that's kind of the only options in the game.
I want to chime in on the threshold. Yeah, I agree. I mean, I agree with Andrew completely. The threshold thing, like people need to understand how blockchain, like validators communities, especially in things that use something like Tendermint or Cosmos or delegated proof of stake, like you end up having like 50 to 100 validators, and then like 2/3 of the voting power is controlled by like 10 people. And those 10 people talk every day, all the time on their own Telegram channel. So even if you use something like Threshold, it's like trivial for those like 10 people to come together and just send the shares if it's an MPC and just decrypt all the data and no one would know, or do like arbitrary MEV and no one would know. So I do think you're really like, there's no way to avoid like mixing some form of teas with threshold like MPC solutions, even if you want to take that route.
Yeah, just want to strengthen both what Andrew and Guy said. One of the big problems with threshold systems is collusion from a larger subset than your threshold. And in particular, you can have these silent collusions where they don't announce anything. They just kind of secretly, you know, try to gain 1%. It's very hard to detect. And so I think one of the things that can actually help here are TEs. And my prediction is that when we have this workshop in a few years, we'll talk about, you know, how MPC and TE work together to solve a lot of problems. But you know, we'll have to wait for another 5 years.
Another interesting angle, I think, I mean, MPC, there's something like, a lot of the MPC are dishonest majority. So you get security with the board, and then in many cases try to do like identifiable boards so that you can pinpoint the bad actor. Now, it might actually be the case that if everyone is running T's, just a bot is fine. But if you have a bot, you already know that something really bad has happened, and you should really stop and analyze. So that's actually a way to kind of trigger and maybe put like a red flag on like a T failing.
Yeah. So just to add on to Guy's question about the like collusions, which can indeed some of those players can perform. It could be that there could be some game theoretic solution as well in that direction, where possibly you, where maybe when you collude, you end up losing somewhere on some kind and in some quantifiable manner. But there is obviously restriction to any of that. But still, that could be one option to consider for sure.
But how do you tackle like silent attacks, like the ones that Itai mentioned?
Yeah, so okay, so you don't want to. So one idea could be you attack one thing that can allow your colluders to attack something else that is of your own, where you reveal some information that could result into some other information getting revealed as well. So or that it could be such that I can prove that it was you who colluded, and then it becomes a race that the one I can, if let's say you and me colluded, either you I prove that you colluded, or you prove me colluded, and accordingly one party wins, other lose. So there could be different models in that kind. Indeed, I personally find that to be very interesting, and we have a couple of papers accepted or in submission in that kind. But it's certain it just gives a range that for sure it provides some kind of a trade-off in some kind. But I agree that otherwise the silent collusion is a very hard problem, no doubt about it. But there could be some ways to actually mitigate it to some level.
Kartik, you made it.
So I think two things that I learned is either use MPC or rely on something like game theory, or use a combination of MPC and TEs. I think that's maybe a one-line summary of what I've learned. Anything more to add? Or is that a summary that we agree with? Mick, please go ahead.
Yeah, so I mean, okay, let's be a little careful here, because we like to go down a very theoretical path on these things in order to, put together as many cool technologies as we can. There's an awful lot of pragmatic issues as well. Like, running stuff on Azure is going to be a hell of a lot more reliable than it is if you run it on-prem. And if your decentralized network assumes that you're running on-prem, well, okay, you get what you paid for, which is you're going to have a whole lot of headaches you're going to have to deal with because the attack vectors just increase dramatically. So if you're not happy with the performance of it, then find a good CSP that supports confidential computing of some form or another, and get a really nice contract with them so that, if things get wonky, then you have external recourse and you can sue them. We like the technology solutions. That's kind of what we do, right? But there are an awful lot of the pieces of a secure system that have absolutely nothing to do with technology and have an awful lot to do with the legal system and the contracts that we have and the institutional trust. At the end of the day, there is no such thing as a zero trust system. There are always roots of trust. We want to minimize those as much as possible, but there are always roots of trust. And so you need to be able to think of the solutions, not just as technology, but in the context of the entire overall deployment that you have for it. Sorry, that's my soapbox for the day.
Thanks, Mick. That was good. I just wanted to actually echo. Well, I was about to say exactly the same thing. Like, if TEs didn't exist, then I don't know. That's the end of it. I guess I'm just going to go centralize the whole thing, so you don't need that trust, or federate it so you put the trust back in the hands of people. So, probably wouldn't even mess with it.
Sounds good. So I guess the fourth part or the fourth approach is think about the architecture and the practical implications of the architecture and your deployment. All right. So we still have about 10 to 15 minutes. So I think I'll open the floor to everyone in the audience to ask questions. Please feel free to raise your hand and ask. So, so if there aren't any live questions, I'll go through my list again.
I have actually one question.
Please go ahead, Nick.
Yeah, where do we find social trust in this overall the ecosystem, right? So you have social trust in centralization versus decentralization, and social trust in terms of who's operating your trusted hardware and stuff. So how does that fit into the what do you think?
Maybe Nick, I can try to start and maybe connect that to Mick's earlier comments about on-premise versus a cloud. I think one of the nice things about I guess modern technology here is that it's pretty easy to move your let's say your secrets from one place to the other. So it used to be, right, that if I had 3 keys that would open my safe, I would hide one, in my house and one, I don't know, in 2 of my friends' house. And okay, that would be very secure, but a dedicated attacker could basically spend a lot of time, surveying my house or my friend's house and eventually gain these keys. So what you do is you get somebody who's very, very good at keeping keys. Let's call that a bank, or if it's maybe a cloud provider, will be very, very good at keeping very secure computation. So you basically can rent, a safe to keep your keys in these cloud providers, and that's kind of the traditional model, right? So you basically outsource it to somebody that will store your keys for you. But I think one of the interesting things about this type of technology is that it's very easy to move these keys around. So unlike physical keys, where if it's in your house and you want to now move it to halfway across the world, you have to physically do that. Here, you can actually, again, using kind of cryptographic means, and you can actually hide where you're moving it to, right? So you can basically move it around the whole world in some sense, and so an attacker won't even know where to try to attack, or where will your key be next. So there might be many different TEs around the world, and it would just try to figure out where those keys are. So there's kind of, I think, new opportunities around that where we just try to say, oh, this is the analog of having a key. Is it better to just store it in your premise, or go to a bank and keep it there? I think these technologies open new types of patterns that may emerge over time.
I mean, maybe I'm oversimplifying your comment, Itai, but is obfuscation the right approach over here?
I think the fact that there are many different TEs, or there will be many, maybe millions or billions, right? And then you can move around between them without even knowing. I mean, maybe an attacker doesn't even know how you're moving it, is something that I've seen explored a little bit, but I think I haven't yet seen. I've seen more maybe on the theory side, but I haven't seen kind of systems try to use this as much. And I think it's an example of the first phase. We try to basically take a physical analog and just kind of adopt it. Okay, we have a key. But here we're kind of saying, okay, there's a new technology. Now we can think about what new things it can open, or what it enables. So I think it enables the fact that if there's many different boxes, and you can actually hide the pattern of how you're moving things between these boxes, that's very different than just saying, I have a box in my house and a box in the bank, and if I need to move it between them, I have to take a safe car that will move whatever I have in the box in my house to the box in the bank, and so on.
So I have a slightly different view at this. I think at next question. So I feel like we need a combination of institutional trust, rationality. We need to take into picture rationality, as well as accountability and detectability. It's some combination of these. If we say, we are only going to do institutional trust, people may not like it because you are trusting centralized institutions. If I say only rationality, that may be good, but I think it is depending on how you model the situation, how you model your protocol, your protocol can be very brittle, because if your assumption fails, your rationality fails, and everything may not go through, right? At the same time, you may want accountability and detectability, but for everything that you care about, you may not have it. So I feel like it's going to be a combination of these three, and depending on the context, the protocol that we are designing, or the application we are designing, how we use that combination, I think, so there is perhaps some amount of art involved. I'm not sure if there's agreement on it, but it's going to be some combination of these three that comes into picture.
So just to throw one more piece in here, that we have to be there has to be, I think, Kartik, this is exactly what you're saying. There has to be this sort of holistic view on it, that it's about sort of the core technologies and what we do for providing the basic technical security that we can. It's about sort of institutional trust as a part of this, and there's an audit role that has to be played for all of this as well. I think one of the challenges we have to deal with is figuring out how all of those pieces fit together, as Itai was saying, in a way that we can actually reason about systems. We don't make, for example, institutional trust explicit in the policy decisions that we're making. And I would say, even to the extent, my favorite example of this is somebody finds, they've got this lovely SGX enclave and they dump an entire Ubuntu distribution into it and claim that it's secure. That the software that we put inside the enclave, we haven't even had the conversation at some level about the behavior of the applications that we're putting inside it and what we understand about what the applications themselves leak for it. All of these pieces have to go into, if you really want to be able to reason about your system, you're going to have to find a way to represent all of these things and put them into a policy. Or the other end of the spectrum is we say, hey, look, we're doing the best we can. The system we have right now allows us to do an awful lot of really interesting computation without overburdening ourselves with expressiveness. I think someplace in the middle between, the formalization and ability to reason top to bottom on it and, hey, look, it just works, is where we need to find the right kind of, again, I'll go back to, it's that cost risk balance that we have to figure out somehow.
Yeah, very much agree with you, Mick. I think hopefully the nice thing about workshops like this is you have people from all the spectrum, right? From operators of, I guess, TE-based blockchains to system researchers and all the way to maybe theoretical cryptographers. And I think all of these, there's a frontier that needs to be pushed in all of these dimensions. It's not as if, one place is the only one that has to move forward. And in some sense, part of the goal of this type of workshop is to kind of have, for people to see kind of the broader view and to think about these, not just maybe, if you're just doing theoretical cryptography or if you're just doing the system design. So you can kind of think about, or if you're just running the network, right? So you can kind of say, okay, there's kind of a larger, I guess, view here and different viewpoints to a similar problem.
I guess that's a nice summary for what we have been trying to do with this workshop. So I think with that, let's maybe end the panel and we'll take a 15-minute break and we'll resume at noon. So thank you all. So thanks to all the panelists and the audience for the questions and the discussion. See you.
Thank you all. This has been an awesome discussion so far. Thanks.
Thank you for having us.
So we'll get started in 2 minutes. All right, let's get started. So in this session, we'll have 2 talks, and our first talk is by Itay Eyal, who's a faculty at Technion, and he'll talk to us about TE Chain, a payment network with asynchronous blockchain access. Over to you, Itay.
Okay, can you hear me okay?
Yes.
Great. Hi, everyone. So my talk today will be about T-Chain. This is a paper from a few years ago. And the main point, I guess the overarching point, is the combination really of blockchain and TEs. This demonstrates the power of this combination. And the context is peer-to-peer payments, so payments directly from one party to another. And doing it directly with a blockchain, we know takes a very long initialization time. We need to put a deposit, and then when we want to issue transactions from one point to the other, we need multiple round trip times to send messages. We'll see the details, but if you know about payment networks, you know that this is a lengthy process. A different alternative may be to do this with trusted execution environments. So one party is going to have its TE commit to moving money to the other party, no blockchain here, just a TE. And then the other party will confirm, and it will have the tokens, and this will prevent double spending, etc. But this boils down to the two generals problem, and money can either be lost or replicated. So this is not effective. But if we combine blockchain with TEs, suddenly we can achieve something new. This is what this talk will be about. So first of all, payment channels, a quick recap. So we have 2 sides in the blockchain, and they each place a deposit amount on the blockchain, and then they can make payments from one to the other directly between the phones or between the devices without touching the blockchain. Now, the important thing and the reason we need the blockchain here is that either party can unilaterally settle the channel between them. So they can go back to the blockchain and prove that they have what they have, they sent what they sent, they received what they received, and then they can walk away with the exact amount that they should be able to walk away with, no matter what the other party does. So let me start with some background on how this can work on a blockchain. So we have here Alice and Bob. Alice produces a setup transaction on the blockchain, and this setup transaction has in it, say, $100. It was created by Alice, but it requires both Alice and Bob's signatures in order to be refunded, and this is time locked. So next month, Alice can go to the blockchain and take the money and leave. So no matter what Bob does, Alice can get her money back. Now, if Alice wants to pay Bob during this month, she can produce a transaction, send it to Bob, and this transaction will pay, say, $3 to Bob, and $97 will go back to Alice. But this transaction does not go into the blockchain, it goes to Bob. And Bob keeps it. He doesn't put it on the blockchain. And if he does want to do so, before the month ends, he can place this transaction on the blockchain, but he doesn't do that yet. And this allows Alice to maybe pay him $2 more. And then she will send him a new transaction sending $5 to Bob and $95 going back to Alice. And Bob will now be able to place this transaction and get the $5 rather than just the $3 if he so wants. Again, this is all until the end of the month, at which point Alice would be able to take the money. So before the month ends, Bob should put this transaction on the blockchain and get back whatever he's owed. And this works okay until the setup transaction is depleted. So until Alice pays Bob $100, and then we're done. And this also works only in one direction. Now, can we do a bidirectional channel, allowing Alice and Bob to pay one another back and forth? So the catch is that we want both parties to be able to settle, either party to be able to settle the channel unilaterally, but prevent either party from rolling back the state. Thinking about it a little bit shows that you can't do this very trivially, but here is a simple solution that does work. We'll simply have two unidirectional channels. So Alice will deposit $100 and Bob will deposit $100, and then they can pay one another, except of course, once one of them pays the full deposit to the other, then they cannot do anything but settle the channel and issue a new one. Even if Alice paid $100 to Bob and Bob paid $50 to Alice, in principle, Alice should still be able to move to send $50 to Bob, but she cannot because her Alice-Bob channel is depleted. The solution to that came from Poon and Drija back in 2016, and it's called the Lightning Network. The idea is to do coordinated state updates. And the idea is the following. A payment from, say, Alice to Bob or from Bob to Alice, this is going to be two-directional, is a capability to close the channel at the current state. So Alice gives Bob a transaction that would allow it to settle the transaction after having received whatever Alice paid him. And it's also a capability to penalize the other party if they try to settle at an older state. So if Alice tries to settle the channel before the payment was made, then Bob can penalize her. She cannot do that because, she can use an older settlement transaction and place it on the blockchain, but Bob will be able to prevent it. So this means that when paying, the payer should give, say, Alice to Bob, a signed transaction settling at the current state. This allows Bob to settle. And Alice gives Bob some secrets that allow him to nullify a deprecated transaction if Alice places an old transaction. And this means that the capability that Alice gives Bob also is abortable with some secret. So the implication is that in order to make a payment, we need to have multiple round trips to form these secrets. I don't think the details are necessary here. And we'll also need, say, Alice and Bob will also need to place a deposit in advance on the blockchain. Enters T-Chain. T-Chain is going to leverage trusted execution environments to make all of this a lot more efficient. The work was done with Josh Lind, Oded Naor, Florian Colbert, Peter Pitzuk, and Guru Sirer. It was published back in 2019. And before going to what teaching does, just an obvious strawman, we might have say we trust TEs completely, then Alice and Bob could interact with TE, but obviously this doesn't work because this is not what the world looks like. The whole issue with TEs and blockchains, what makes this interesting to us, is that someone should operate the TE. So really it's Alice and Bob interacting with some Carol who has a TE, and this gives Carol total power over whatever funds the TE control. So this is a no-go. The crux of TE is as follows. We're going to have the trusted execution environments keep secret keys that the owners of the money do not control. So the TEs will maintain the secret keys. Alice's keys will be maintained, generated, and kept inside her TE, and respectively for Bob. And the TE will only produce a settlement in a channel. So this will prevent, for example, settling for an old state. And we'll have the TEs form a secure channel between one another. And they'll create a private public key pair with Diffie-Hellman and use attestations on each side verified inside the TE, so that each TE is confident that it's speaking on the other side with a TE. It doesn't know that it's Bob's TE, but Bob will have to verify various things in order to make sure that he is not cheated, and vice versa for Alice. So this is going to work as follows. First of all, we need deposits. The basic structure is still going to be deposits on the blockchain. And the idea is that Alice will have her TE generate a blockchain address, and it will send money to the TE address. Of course, the TE is not aware that money was sent to this address. So Alice will notify the TE and prove to the TE that, or not prove, but tell the TE that these deposits are on the blockchain. The TE cannot verify that this is really on the blockchain. It will be Bob's responsibility to verify that the deposits relevant to him are actually on the blockchain. Now, when Alice and Bob wish to form a channel, then Alice is going to associate a deposit with the channel. And this is something that was not possible without TEs. Without TEs, Alice and Bob had to first communicate and then decide on whatever they needed to decide, and then create the deposit that was secured by both their private keys. Here, the TE secures the deposits, and so the deposits are placed on the blockchain, say, last month. And now, when Alice and Bob wish to form a channel, then Alice should instruct her TE to associate the deposit from last month with this channel. So we have a red channel here. The color is not important. We're going to have only this red channel for this discussion. And Alice is going to instruct her TE to associate the deposit with the red channel. And Bob will confirm that and look at its record of the blockchain and see that the deposit really exists there. And this can be done instantly. There is no need to wait for anything to happen on the blockchain. There is no blockchain operation here, just looking at the records. Now, after Alice and Bob associated their deposits to the channel, then they can instruct their TEs to pay the other party. And the TE is going to update its local state that the payment was made and produce this sort of receipt that Alice can send Bob. And once Bob receives this message signed by the TE, it knows that Alice's TE has completed this payment. Alice will not be able to settle at an earlier state. And Bob can send this payment into its own TE, and the TE will be updated and will be able to settle the channel if Bob requests to do so using the deposits. Now, each TE can settle the channel using the deposits that were associated on both sides. And note that once the deposits on both sides were associated, then maybe Bob will be able to settle just with his own deposits. Maybe he will also need to take something out of Alice's deposits. And once the settlement transaction is created, no more payments can be made. Now, there is an additional benefit here, and this is that we can dissociate deposit. So if Alice doesn't need one of the deposits because it's not used to secure any payment she's made, Bob is in debt to Alice and her deposit is not necessary anymore, she can ask her TE to dissociate this deposit, and then the deposit becomes available for other payments. This, of course, requires the TE to get a confirmation from Bob. So the TE will request confirmation from Bob. Bob will say, okay, through its TE, I don't need this deposit to settle. And then the TE will allow Alice to dissociate the deposit, and she can subsequently use the same deposit for a different channel. And this represents a significant saving because every time we need to actually touch the blockchain is expensive, both in time and in money. So and of course, if Alice wishes to dissociate a deposit and Bob does not cooperate, then Alice can still settle with the old state without losing any money. But she will have to access the blockchain to settle the deposit. Now, the key point here is that there's, I guess, two key points here. One is that the blockchain access is asynchronous. So once the deposits go on the blockchain, we are not limited by time. I said before that we have a timeout, and after 1 month, Alice can take her money and leave, and then after 1 month, they'll need to set up a new channel. Here we don't necessarily have that. We don't need to have that because the TEs secure the deposits until they are instructed to settle. So we don't rely on the speed or lack thereof when accessing the blockchain. This applies both to payments and to all the deposit actions, including settlement. This also means that we can instantly make payments. So if Alice and Bob meet and they already have deposits on the blockchain, without accessing the blockchain again, they can immediately set up a channel and complete a payment. So to prove the correctness of all of these, we define what we call balance correctness. I'm not going to go very deep into the proof, but just to give you an overview. First of all, we have the perceived balance. This is what the user understands as their current balance. It's their initial balance plus whatever they received minus whatever they paid. And there's the blockchain balance, which is the actual balance written on the blockchain. And when settling, the user moves their perceived balance to the blockchain, and it should be the same. The proof actually has two elements. One is a simulation-based proof. The first side is a hybrid world with a TE and blockchain functionalities. Those existed before, nothing new here. And we show that this is indistinguishable to the environment from a world with a TE ideal functionality and the simulator instead of the adversary. Actually, nothing fancy here, just painstaking details. But then, and this doesn't always happen with these sort of proofs, we actually had to prove that in the ideal world, we actually get what we want. So the thing we want to prove is that when a party wishes to settle, it's able to move eventually, because we are synchronous, it's able to eventually move all its funds from the perceived balance, whatever happened in the payment channel, into the blockchain balance. So first we need to prove that this protocol completes, then that the functionality maintains the invariant that the perceived balance is what we call the actual balance maintained by the functionality, and that after the completion of the protocol, which we prove completes, the actual balance is indeed what happens on the blockchain. Again, I'm not going to go over the details here. And I would like to mention that we implemented this and the performance is fantastic. In particular, we're able to do so in Lightning to get reasonable performance because of all the back and forth, and you need to complete each payment before making the next one. The performance always relies on batching, and we're in T-Chain we're able to do this without batching. Because we can send multiple payments over the air concurrently, and they can be fed into the T on the other side, one after the other as they arrive. We ran this across the Atlantic from Cornell to Imperial, and we got very quick performance. I actually want. Yeah, the time will allow to go through something else, which is, I think, more interesting, which is multi-hop payments. So the title said that this is going to be a payment network. And so far, we only talked about point-to-point payments. So how can we make a network out of this? And the key thing to implement here is actually what happens when Alice wants to pay Carol, but she goes through a middle step, which is Bob. So Alice has a channel with Bob of the construction I described before, and Bob has a channel with Carol, and Alice wants to pay Carol, and no one should be able to steal money, and everyone should be able to settle at any point, getting whatever they should be getting. So the Lightning network, that Lightning network from before uses HTLC to implement a multi-hop. HTLC is a construct that requires knowing a secret, a pre-image, and being able to sign in order to take money before some deadline. After the deadline, the money goes back to whoever sent it. And this allows them to construct a multi-hop payment. The idea is that Alice creates an HTLC payment to Bob, so Bob can take the money before time T by knowing a secret S. After time T, the money goes back to Alice. And then Carol can take the money from Bob if she knows the secret S, and she can sign as Carol before time T-1. And again, after T-1, the money goes back to Bob. The point is that Carol generated, and she's the only one who knows the secret S. So she sends the hash of S to Alice. Alice and Bob can now generate their HTLCs. And if Carol takes the money, she does so before T-1, revealing the secret on the blockchain, allowing Bob to take the money before time T, and everybody is happy. And this works well, but it is very time sensitive, meaning T and T-1 should be in units that are large enough to make sure that everything goes on the blockchain and everyone can see and create the next transaction. We want to be more efficient than that. And that turned out to be non-trivial. We're going to make it. So the protocol, the payment chain, hence the name T-Chain, is going to require no blockchain access or monitoring beyond the deposits that we had initially. And any party should be able to settle at any time, like I said, and there is going to be a period in time where it's not clear whether we are before the payment. We have here Alice, Bob, Carol, and Dave. So either before Alice paid Dave or after Alice paid Dave. So it's going to be atomic, and it's going to settle either before or after, pre or post. Now, to do that, we're going to use two types of settlement transactions. They're going to be local settlement transactions. So if Bob does the local settlement, then he only settles his own deposits locally. But there's also going to be a chain settlement. So there's going to be a point where Carol has a single transaction that settles everyone's channels. And of course, these conflict. So if Carol settled everyone's channels, Bob cannot do a local settlement. The global settlement, the chain settlement, also settled his own deposits. And vice versa. If Bob completed his own local settlements, then Carol cannot place the chain settlement transaction. And this is going to allow us to do what we need to. And this is going to work in multiple phases. So phase one, we're going to lock the deposits and actually the channels. So once a party locks the channel, it will not use that channel for anything except for this multi-hop payment. And it guarantees that this will be locked, and it generates this global chain settlement transaction. It is not signed yet. It's just formed, having everybody's addresses, etc. And then the next step, we're going to sign this transaction. Now we have this transaction, it's not signed yet, so every party signs this transaction. At the end, Alice has the signed transaction. In principle, at this point, she can settle the system with this chain settlement transaction, and everybody's happy because it's settled in a fair state. And now something non-trivial starts happening. Now each party is going to promise not to settle its local payments in a prepayment mode. So after sending the message promised A, and the TE is going to enforce this, Alice, then Bob, then Carol are going to promise that they're not going to settle local channels unless someone else has. And someone else might do that because, say, Alice promises not to settle prepayment, but Carol still hasn't committed. So Carol might now settle prepayment locally, and then Alice can give the prepayment settlement that Carol placed on the blockchain to its own TE, and Alice's TE will allow her to settle prepayment. And then once we reach Dave, then everybody promised not to settle prepayment unless someone else does. But once we reach Dave, we know that this is not going to happen because no one is going to be the first. So now we can go back and promise not to settle post-payment unless. So everybody is going to update its local channels to its post-payment state, but promise not to do that. So each of them promised not to pay in a post-payment state unless someone else does. Now, when we go in this direction, still nobody is going to do this because not everybody's committing not to do that. But in the next state, someone in state 5, someone might settle post-payment, and this will allow, so Alice might settle post-payment, and this will allow Dave to also do that. Finally, we're going to erase the chain settlement transaction, the big one, because we want to release the channels back into the wild again, so allowing the different parties to use them at their own will. So each party deletes its chain settlement transaction and notifies the next one, and then it percolates back, and each party tells the other parties that it has now erased the global chain settlement, and so they're able to release their local channels and use them as they will, because no one is able to take them away with this old chain settlement transaction. And we've now completed an atomic Alice to Dave payment without touching the blockchain, and anyone can and could have at any point settled in a legitimate way. And this is T-Chain. So we trust the hardware manufacturer for this. And then we're able to do off-chain initialization and settlement. We're able to pay with a single message. We get high bandwidth, and we can do payment chains. The next step, I think, probably is an extension to general smart contracts, and doing that without giving control to the smart contract to a single party running the TE, but really doing it in a distributed way and yet efficiently. This is an open question, but overall, I hope this demonstrates the new kinds of things one might do with when combining trusted execution environments and blockchains. Thank you very much.
Thanks a lot, Itai. Questions for Itai? Arvind, do you want to?
Sure. Right, just a quick question. So in your payment channel network, so all the users in the payment path, do they have to use TEEs, or what happens to balance security or whatever if one of them doesn't have a TEE?
The answer is absolutely. So you're talking about this slide, yes?
Right.
Yeah, so absolutely. This is T-chain in every step of the way. So what enforces the promises, which are crucial for the entire thing, is that each party does not actually control its secrets or the settlement transactions. They're all contained inside their TEs.
Right. Okay. Good. Thanks.
Itai, please go ahead. Itai Abraham.
Maybe I misunderstood, but what are the standard problems in the payment channel that I have to pre-fund the channel? Let's say I'm paying Kartik, I have to pre-fund $100. So did you actually think maybe about modifying the scheme so that I can basically like pre-fund the TE, and then I can, from this pool, I can pay different people. So that would be different than maybe Lightning Network, and it would also maybe eliminate the need for a multi-hop, because I could basically like, find the TE I want to pay and just pay that TE.
Yeah, that's an excellent point. We did not do that in this work. I don't think it's trivial, because the implication is that the control of a deposit might go recursively from one party to the other. So if A pays B and B, C, and D, and say D owes A, and then A owes someone else, then suddenly that someone else might need D's deposit in order to settle, So there is a different type of dependency there, and that would require more thought. This is the reason this wasn't included in this work. I guess this also relates to the extension to more general smart contracts, where we have multiple entities interacting with the same state. It might become a bit more delicate. Yeah.
Yeah, I can imagine like almost like a layer 2 solution where your funds are locked between the multi-signature of yourself and the TE, and then you can basically either transact here or there almost seamlessly.
Yeah.
All right. Thanks a lot, Itai. Guy, do you want to share your screen?
Yeah, thanks very much.
Yeah, that would be great.
All right. So our final talk is by Guy Zeiskind, who is the founder of Secret Network, and so he's going to talk to us about Secret's journey, about the lessons they've learned past 2.5 years of running TEs in production. Over to you, Guy.
Thank you very much, Kartik. So first of all, apologies. I'm still recovering from a bad cold. So I have my tea here, and I'll do my actual tea, and I'll do my best. So yeah, so Secret Network, really, we are a blockchain, and we're using TEs pretty much all around, but just for privacy. We're not using them for correctness. We're using just normal, plain vanilla Tendermint consensus to achieve correctness. But we did determine that it is the best current solution to achieve smart contract privacy. Now, why is privacy even interesting? Again, this is probably not the audience to explain this because everyone here understands it, but generally speaking, beyond privacy being very important and a basic human right, it's also something that we usually take as a basic property that just exists. Listen, beyond Web3, we just assume that there is some form of privacy. For example, if you go online and play a game of poker, not on the blockchain, then you at least assume that the server running the code won't start sharing your cards with the other players, and you take comfort in that. However, in an environment like a blockchain where everything, and I do mean completely everything, is public for everyone to see, you can't actually implement something like a game of poker unless you have other privacy-preserving primitives. So that is really the motivation. And this obviously stretches to so many other use cases that I don't think we've even covered the tip of the iceberg. So I've been working on this for quite a while. I'd say almost a decade now. First as a grad student, and then in production. Generally speaking, the problem that we've been trying to solve is that of how do you achieve secure or private computation on the blockchain. And if anyone doesn't see the connection immediately, then this is basically the equivalent of implementing private smart contracts. So smart contracts kind of give us like half of secure computation. You get correctness, but they don't give privacy. Now, how do we add like the other half? Like what tools do we have to add the other half? So we actually achieve private smart contracts, which actually achieve secure computation, which is both correct and both private. And by private, I mean that the inputs are generally always encrypted, and users can know that only they actually ever see their inputs. Blockchains, as you know, are a multi-user system. State, which is another form of an input in the blockchain space. Every computation is stateful. So the contract is a state, it's a database, it is served as another input. So that needs to be private. And it's also an output, so it needs to always basically be end-to-end encrypted. And then sometimes you want encrypted outputs from the contract, and sometimes you want the outputs to actually be revealed to everyone. A simple example is a voting contract. So a voting contract, ideally you want the votes to always remain private, but you want the tally, the output, to actually be public. So you gotta give that granularity to the developer to decide based on the use case what information or post-process information is okay to reveal. And that is exactly what we're doing. And before I get to how we're doing it, which is a big surprise, using TEs, as I'm sure people here know, there are basically, I'd say, two techniques to solve this, right? You either use a form of MPC, which we touched on the panel before, and that MPC can be secret sharing, garbled circuits, or it could be some form of threshold FHE or multi-key FHE or something like that. Those will probably be much slower, but clearly you can use those. But as we touched before, there is actually this issue of collusion, because in a blockchain network, you have the backend, the servers are validators or miners, And if they collude, then all bets are off in MPC. And the problem with MPC is silent collusion, as people pointed out. Even like the validators may be able to collude, but no one will be smarter and know that. So yes, you can solve that with cryptography, but there are trade-offs there as well. And the other solution is to use Ts, but then obviously you have to trust the hardware. And just for completeness, I'm putting ZK here, but as I'm sure people here know, ZK aren't really a solution to secure computation. Like you can't use ZK to do a sealed bid auctions smart contract where the bids stay private even after the fact. Like you need one of the other tools. So that should be clear to people here. And for pragmatic reasons, and especially when we build secret, we focus on Ts alone. So as I mentioned, like I started this project as a grad student, but then going from a research paper and a really bad prototype to a system that needs to stay functional for years and under all situations is much harder. And it took us a few years, but in 2020, we launched Secret Network. It's the first blockchain with private smart contracts. It's been in production for like 2.5 years, and it's seen quite a lot of visibility. It's not by any means one of the largest blockchains, but it's a fairly sized, medium-sized blockchain that has seen a lot of developer and user activity. And this is interesting for two reasons. A, because for the first time, we gained a lot of insights about what it means to put a system in place, an open system, where you can actually do things like secure computation, like running computations over private data. The other part of it, the less, maybe not the prettiest part, is that obviously when you get into production, then you start to see all of the things that you didn't think about before you went to production. And that leads to a lot of problems, and it leads to attacks, and it leads to a lot of things. And those are also part of the insights that we gathered along the way. So very high level how Secret works. Essentially, it's a Cosmos-based blockchain. So it's just running tender-mint consensus between something like 100 validators. This is a design choice. Like we decided not to utilize Ts for anything that relates to integrity or correctness. We are using pure consensus for that. But actually to achieve that, we had to make sure that the different nodes that are running the Ts, everything that they do does not break consensus. And the way we basically did that is make sure that every validator in the network is running a T, but there is some kind of registration process, there's some kind of key sharing protocol where all of the Ts basically prove to everyone else that they are running a valid T. The remote, they join the network, they run some code, they generate new keys, they prove via remote attestation that these are like the right Ts and that they are patched and everything that you want. And then the other validators basically share from their Ts to the new join validator the secret key material that they would use to derive the network key. And then users from the outside, essentially, when they want to send a transaction that executes a smart contract, they can use the network key to basically encrypt the payload. So they encrypt all of the inputs to the transaction, and they broadcast that to the network. And then all of the validators, they take the block with the transactions, which are, their payload is encrypted, they push it into their Ts, and inside of the T, the actual execution happens. And then if the T needs to encrypt the outputs or update the state and re-encrypt it, then they do it. But because everything is done in the same way, we don't break consensus, and the nodes and the network can reach consensus on the blocks. Now, this design choice, and I do want to touch that, we'll touch more challenges, but as some people know, and if you don't, then I'm gonna shed some light on this. This design choice essentially means that you're replicating the same secret key material across all validators, across all keys, across all nodes, which means that all it takes is breaking one of those keys to actually decrypt data in the network. So, and this is a known trade-off. And I think some people would argue that, okay, why not compartmentalize this in a way? Why not limit, for example, why not put a minimum stake, right? Like only validators with $1 million plus in stake can actually get the key material. Or why not start sharding the keys in some ways? There are many trade-offs and dark corners to doing that. We are working on implementing some of these mechanisms, but I also want to put some light on the social aspect related to this. So Andrew Miller, who's I'm sure you've heard from his talk, some of those dark corners, he actually put this in a discussion in our forum. Hey, why don't we limit who can actually share the network secret key? And the problem, or the good thing when you have an actual active network, is that people have their own opinions, right? And people actually, even though from a pure security perspective, if we were writing a paper, then this is the obvious answer. But now you have a community and stakeholders and people who are building on the network, and some of them are basically saying that they don't think that limiting who can get access to that key material in their keys is the right approach, because decentralization, because of commercial and economical aspects. And I do feel that it's very important, especially for this audience, to kind of show that those issues there might be a fairly easy technical answer, but when you're thinking about the other aspects, it's not actually as clear. And by the way, I actually do think that we need to compartmentalize, and even within the core devs, I think I'm in the minority. But going back a bit more high level, I do want to kind of pinpoint a few of the things that people have built on the network and how they utilize privacy in interesting ways. So I hope you can hear the sound. I will do my best. So one cool thing in Secret is we have a standard for what's called secret NFTs. And basically NFTs on any other blockchain, because blockchains are public, the data is public. So there's this common joke that everyone can right-click save your NFT content because it's up for grabs. And Quentin Tarantino actually met with us, and he didn't understand technology, but he did understand enough to say that he does not understand the value of NFTs if everyone can immediately copy the entire content. And obviously in our network, we came up with a solution where only the owner has the NFT metadata is encrypted, and only the owner can actually get the decryption key because he's proving ownership to the contract. And with that, we built a project with Quentin to basically digitize the original Pulp Fiction screenplay. So we took different scenes from the original screenplay, and Quentin swears that no one has ever seen the original screenplay in 30 years, and we turned those into these kind of like encrypted NFTs. I'm going to show a very quick example of what it looks like. Actually, can people hear this? Can people hear the sound? No, okay.
This is Quentin Tarantino.
Okay.
And I am talking to the purchaser of the NFT of my original handwritten manuscript from Pulp Fiction. This is the last scene in the film.
So then after Quentin came to us and we completed that project, and by the way, if you're interested not just about the technical issues, Google that thing, you'll see that there was a lawsuit between the studios and Quentin about the rights to do this. It was a whole thing. But after that, another famous director, Kevin Smith, came to us and said, you know what? I want to do the same thing, but instead of releasing a screenplay, I want to release a full movie as an NFT. So basically, we did this. It's a movie called Clear Was Here. And the only way to really get access to it was to mint an NFT. And then in that NFT, you had a decryption key that only the owner can get access to. Plus, you had each NFT had like different, like behind the scene content, but each one was different. So like if you got two, then you get two of the same movie, but you got like more and more content. People started to collect that. And that was pretty cool. It was kind of like a pay to access to a movie using Tease as the backend to protect that movie. Moving on to a very, very different kind of use case. In Secret, you have the ability to basically do ERC-20s, but that are private. Now, let's say that based on Andrew's recent talk and let's say attacks, then I'm gonna call them privacy enhancing and not privacy preserving, because there are actually side channel attacks that are not related to the T's, just by like observing access patterns and that, then you can actually, for example, probably harder to de-anonymize amounts. So you get confidentiality, at least most likely, but sender receiver privacy, for example, those guarantees are not as good, and we're launching an upgraded version right now, but there's more work to do there. But generally speaking, on Secret, there is a vibrant privacy preserving DeFi ecosystem. This is an example of one protocol.
The first step to do this is go to the wrap page and convert some of your secret to secret. This is a very important step because on Shadeswap, it only deals in SNP 20s. It doesn't deal with regular secret. So be sure to convert some secret to secret in advance of the Shadeswap testing. And from here, as you traverse the bonds page, the derivatives page, any of the pages, you can create a bug in the bottom right corner by clicking on the support button. You'll see here I'm running through create the viewing key for secret and what that will look like for some of you.
So part of what you've seen, they're creating like viewing keys, like in Zcash. So basically, the balances and everything is encrypted, but the owner can generate a viewing key, for example, for the dApp to actually get access to see some data, or you can create a viewing key to send your CPA for accounting purposes and whatnot. And the last example I want to share is a protocol that's basically built a private payment / private messaging application on top of us.
Welcome to the Alter Network. This platform is designed to give you freedom of speech, to be able to share anything privately. The Alter Network protects your identity. Here, you remain fully anonymous. Alter Network is a place where data collectors and data centers are powerless. Alter is a decentralized communication platform that cannot be stopped. The network is owned by people just like you and me. Alter does not control messages and files that are distributed across the platform. Alter is simply the user interface that enables our users to communicate with one another in a trustless, decentralized manner. Alter Network is a firm believer in the saying, not your keys, not your data.
And really, there's a vibrant ecosystem building all kinds of use cases. But I wanna, in the interest of time, move to the challenges. So like, to me, these are interesting because like when we came up with the protocol, we didn't think of those use cases. And an important part, in my opinion, is that I think we're just scratching the surface. Like, had blockchains had privacy, and these are obviously probably the best practical, still the best practical contender. There's a lot of things that we can do that we couldn't do before. But obviously it's not all good. And part of the reason we're here is because T's are not trivial. They don't just solve the problem for you and you're done. There's actually a lot of concerns around T's And there are a lot of problems, as I'm sure everyone here knows. Hold on a second, okay. And some of the problems, and I'm gonna go very, very quickly, some of the problems with these, I mean, most of the problems with these are probably related to side channel attacks or just implementation bugs like we saw with Epic, which was disastrous. But probably, and I actually hear two different opinions on this from researchers. Some believe that these are finite, or you can kind of converge to a point where it's like very minimal or very expensive to attack. And the other are like, no, this is inherently part of Tease. It's always gonna be part of Tease, and it's always gonna be a cat and mouse game. I don't know what the right answer is, but there are two philosophies here. But in any case, right now, we do have vulnerabilities like once a year, twice a year. Some of them are disasters, some of them are not so bad. And the process to recover from these, in my opinion, right now is the biggest issue. Intel calls this a TCP recovery process, which is basically means that once the vulnerability is disclosed, there's a patch and there's a period of time where you get all of the vendors, OEMs, providers, service providers, CSPs, all of them to apply those. And after a certain time window, Intel attestation service would start basically reporting enclaves that try to attest but are not updated and patched. That time window is disastrous in the sense that, like in an open network like Secret, where people are running blockchains, you can't just announce a 0-day and then wait 6 months to close it. Like that's just a no-go. And a lot of what we're doing right now with basically kind of like our own like emergency breaks measures, key rotation, all kind of things like that are really about closing that gap, which is very serious. But ideally, I do think that the most important solution for the long term is to have more hardware providers, and to be very frank, not just like enterprise companies like Intel and AMD and Amazon working on their T's, but actually have startups like we're seeing with ZK accelerators, actually building open source T's in the open, testing them and iterating much faster. To me, that is likely the best solution. Until then, the only solution is really defense in depth. Some use cases, for example, we're mixing in MPC to kind of distribute the trust so that you would need to break much more than a single T. We already talked about limiting access to keys, and there are many other ways to think about. I'm gonna skip this one just in the interest of time. I do want to touch one more thing. So one cool thing that we're doing now, and there's several companies and design partners that are working with us on this, and I'm really excited about, is this idea that we call unstoppable wallets. Basically, it's an MPC wallet or a threshold wallet where a user or a set of users can co-sign a transaction, and that could be an Ethereum transaction, doesn't have to be related to Secret, with the chain. So you have a smart contract on Secret that is a wallet smart contract. That smart contract only has a single share, and then if I'm a user, I would have the second share, or if we're a group, we would have the other shares of the key. And why is that interesting? It's because the smart contract is obviously programmable. So now you can think of all kinds of interesting use cases that leverage this building block. For example, the most trivial one is to basically do a spending policy, right? Like I can only spend 1 Ethereum a day. If it's more, raise an alarm or do something, or because probably someone hacked my account, right? Another interesting use case is like DAO vaults. So today DAOs are governed by multi-sigs. Usually there's a DAO, everyone has a vote, but that vote doesn't matter because there are 5 people who are doing the multi-sig, and they can spend all of the funds whatever way they want. Well, what if alongside the DAO, the community programs the contract with the spending limits and spending rules,
such that the DAO participants can actually abuse their power. And another interesting use case is actually direct wallet exchange. So, today I can sell my Bitcoin, I can sell my Ethereum, but there are many kinds of OTC deals where you want to actually sell an asset that might not even exist yet. Maybe I'm a VC who bought like $100 million in a token that is only going to launch in 2 years. Well, I want to just sell that wallet and that eligibility while proving that I lose control when I sell that wallet. And with an MPC wallet like that, and plus some share refresh mechanism, you can do that. And this is the final point. The problem with this solution is that if you look at all of the state-of-the-art threshold ECDSA protocols, which is really what you want to implement here on chain, they are way, way too slow. They require multiple rounds, which means multiple serial transactions. We ran like some tests, and if we even tried to do that, it would be like doing one threshold signature would probably fill an entire block on Secret today, and it would be completely impossible. So we had to kind of rethink the algorithm to do threshold ECDSA in a way that is on-chain friendly. And we got some really amazing results here. We got like, I think somewhere between like 10x to 100x speed up on our parameters. And the chart on the right, it shows you the gas cost. So 500,000 gas on Secret right now is less than half a cent. So for each party to generate, like even if you have like 15 parties, like with our threshold ECDSA without implementation, it would cost less than 1 cent per party to generate a signature. And it would only take one transaction by each party, which is really a significant improvement on the state if we use any of the other state-of-the-art protocols. And actually, this is so efficient, and I didn't believe we'll get to that level of efficiency, that if you look at just like simple DeFi swaps or secret NFT or like NFT mints on our network, they are more expensive than running this MPC protocol on chain, which is pretty cool. And with that, I'm gonna stop. Like, there's a lot of interesting research questions. Like, T's don't solve the problem. There's hopefully, if you get anything from this, is that computation, like secure computation on chain is important. T's are a valuable solution, but there are a lot of challenges and open problems. Many of them are on the research side, and we would welcome any type of collaboration, conversation, and improvement. Thank you.
Thanks a lot, Guy. Questions? So I have a question. So you did mention this notion of just having one secret that is shared by multiple different parties, and anyone can get it. So I think if you think of it from the perspective of attack surface, clearly that is perhaps not the right way to go about it. But you explained the social side of things, and where people do believe that is how it should be. So I wonder, from a governance standpoint, or when protocols are designed, how do you think about managing both aspects?
So two things. A, when you start a community, then you can make a lot of design choices, and then you see if a community is forming and is embracing it. If you made the wrong design choices, but it's not just design choices, right? There's a lot of things going into building a network. Then community will not come. But assuming they do come, usually what you set in the beginning in T0 is going to be accepted. The problem, or not a problem, the actual nice thing is that once the community grows and the initial decisions have been set, then now that the community has a voice of its own. And usually, just like any governance, like any social system, then you have a lot of stakeholders you need to take into account. For example, just to give a very concrete example, like if we were to now limit the ability to join the network, then it may be much harder to attract all kinds of service providers like wallets, like people who are running like infrastructure to query. So like as once these things are already formed, it's much harder to change them. How to balance them? I don't know. I just think discussion and openness. Like I don't believe in vetoing. I believe in giving different options, talking about them, and hopefully conversion to a good solution. But it is much, much slower. Like now that we see that the community is divided, like on this point, then we're thinking about other solutions that are some kind of a middle ground between the two.
Thanks, Guy. Aniket, please go ahead.
Yeah, so my question is also more on the one aspect. So because we can employ T for confidentiality and privacy to some extent, and it's not always that the regulation find that to be attractive. So I was curious, because you're running this for a couple of years now, how is your interaction with the regulation across different parts of the world?
I'd say it's been very minimal, to be honest. So I've had a few conversations with regulators. It's usually been high level. Some of them get it, some of them don't. I'm a bit frustrated about it, to be honest. Like I want to talk to regulators. I want to be like, I mean, I've not a lot of the conversations with regulators, and we have this like I guess forum going on called the Universal Privacy Alliance with Zcash and others. So we are trying to create like an outreach to regulators in those platforms. But my frustration is that the conversation usually, they come and go, they stay very high level. And honestly, as technical people, I'm not sure how to resolve it. Like, because this, I mean, the technology exists, right? Like, as long, like people should know if you're putting something like backdoors or no, and there shouldn't be backdoors generally, but if there are, people should know and be able to audit the contract. But there could be different implementations on the DApp level, right? Some of them are, let's say, more regulator friendly, some of them are not. Maybe we as a core company, because we're docs and people know us, we will only deal with the, let's say, more regulator friendly approach. But the conversation, it's too shallow, fortunately.
All right, maybe we'll just take this one last question. Andre, do you want to go ahead?
Yeah, sure. Thanks for the talk, Guy. And I find it really fascinating to hear from your insights and hear from the rest of the community chiming in on all of these. It's been really interesting. I wondered if on those lines you could expand more on what you're seeing of smart contract developers face. I mean, I guess this was true of Oasis too, but I found it really interesting kind of understanding like, okay, what's the right kind of interface? Do we need to think of smart contract developers as completely just copy paste from a plain text blockchain? Or is there some level of, I don't know, are they ready to dig in and, you know, take on some of these access pattern issues from the contract side? Yeah.
I mean, is the question, can smart contract developers take some of the load and make some of those design decisions themselves, or?
Yeah, and what's their appetite for it? Have you seen?
I haven't seen any appetite to date. It's actually, and this is not surprising, right? Developers want things to be as easy as possible, as scalable as possible, but they want privacy. They want, you know, to have their cake and eat it too. And again, I would probably be doing the same thing in their shoes. I do think that we need to give them options, and we need to be, and part of this is with the work we do, we need to be very clear about what they get and what they don't get. Maybe that would actually incentivize smart contract developers to do that. The other problem that I see is that just like smart contracts on Ethereum, right? It opened up a can of worms because you have all these vulnerabilities, even if you do audits, even if you do formal verification, like there's so many places where you can, like bad things can happen. And here, I mean, the smart contract developers, they don't understand the privacy nuances in many cases. And by the way, they shouldn't. Like we should do a better job or try to help them. but take something as simple as an AMM. An AMM, like for us, it was obvious that if you build an AMM, the inputs might be private if the tokens are private, but once you trade on an AMM, and unless there are many trades in the same pool, in the same block that kind of obfuscate each other, anonymize each other, then I can just look at that contract, look at that block, look at how the pool weights have changed, and basically infer what the transaction was. But smart contract developers, they don't understand that. They don't understand the trade-off to even get close to thinking of those issues. So the long story short is that if you want to build privacy into your smart contracts, you really got to understand the pitfalls because there are many.
Thank you.
All right. Thanks a lot, Guy, for the interesting talk. And with that, we conclude our day 2 as well. Thanks a lot to all the speakers, the panelists, and the attendees for making this an enjoyable learning experience. See you.
Thank you very much.